Are we on?
Yes.
Okay. It says we got 13 minutes and 45 seconds left.
I'll fix it, don't worry.
Okay. I really had to talk fast. Okay, I've got two homeworks to return. Bartholomew and Stefanov. Here's the official university roll. So let me pass this around, and you should sign your name to this. If you're here, if you're not, I'm not sure what you're supposed to do. I have to turn this in, and this is, I guess, determines whether or not people are officially attending. Anything. Used to be,
Dr. Cooper?
been getting these things for years. I would just throw them out. But this time they wrote urgent across the top. We were getting much more bureaucratic. So
Treasure Coast has a question.
Treasure Coast has a question. Go ahead, Treasure Coast.
Do you want us to sign something, or?
I don't hear the question.
Do you want them to sign something also?
Can I do it over the air? I don't know. If I have something for them to sign, I'll send it up there. There's only 3 of them anyhow, is that right? So,
Yeah, there's only 3.
so we can work it out. Anyhow, all I'm doing now is just passing around this thing I got in the mail from the university administration, from the registrar's office. Okay, homework 0 is due the 25th. Are there any questions about that? Remember, if there are minor details you don't understand, then just ask me. But if you have no idea how to handle something like this, then you should find yourself a tutor or somebody from the math department who'll help you out, because this is important in the sense that if you don't understand it, then the rest of the course, the second 2/3 of the course, are not going to make any sense to you. So this is just a review of what you're already supposed to know. Other than that, I'm ready to go unless there are some questions. So the last thing we were talking about, I think I introduced the notion of conditional probability, which is in Chapter 3, and I think I gave this definition, which is on page 76. So let me start with that. So this is our definition, and it's equation 3.3 on page 76. It's the key to this chapter 3, conditional probability and independence. And the equation is this. It says the probability of some event A given another event B, the vertical line means given, is equal to the following. The probability of the intersection of A and B divided by the probability of B. So that's what the author gives in the book, but it's not especially well motivated. And the basic idea is this. You've got this sample space, and in it you have 2 events, A and B. So that's A and that's B. And the question is, when I conduct the experiment, what's the probability that A will occur? In other words, that one of the points that's in A will occur if I know, I'm given the fact that a point in B is going to occur. So right away you can see that if you know B occurs, then the only way that A can also occur is that the point that occurs is going to be the one that's in the intersection between A and B. So in effect what you're doing here now is you're giving additional information. And the question is, how do you handle that additional information? And it turns out that at the beginning we'll see that it's sort of obvious, but then it can get tricky fairly quickly. And what you can see here is that if you are conditioning on the event B, then that means 2 things. One is it means that you must lie in the intersection of A and B, and the other is that nothing outside of B can occur, because you're already saying that when the experiment is performed, something in B occurs. So in effect what you're doing is you're taking the original sample space and you are changing it. So now there is a new sample space, which is B. And so all of the points that were outside of B have to have their probability set equal to 0. You're defining a new sample space. And all the points inside of B have to have their probabilities changed, because if B is now the new sample space, that means that the probability of B must be 1. So what you do is you set the probabilities of the points outside of B to 0, and the probabilities of the points inside of B are all inflated in such a way that they stay the same relative to each other, but now the sum of their probabilities is now 1 instead of whatever it was before. And the probability that A occurred, if you know B has occurred, is then the probability that a point in this new sample space occurs, which is in the intersection between A and B. Okay, so I'm going to give some examples. We'll see how that works. There's another way to look at it. I can rewrite this equation this way. I could say the probability of AB is equal to the probability of B times the probability of A in B. So all I did here was multiply this out and then reverse the order. And now if you take the frequency point of view, you could say the frequency or fraction of trials with which I get a point that is in both A and B in the intersection is equal to, first of all, the fraction of time I get a point in B multiplied by the fraction of time I get a point in A if I got a point in B. So with that interpretation, then you can see that if I started with this, I could work backwards and get this, but ordinarily this is taken as being the definition. In fact, in the book, this is equation 3.3, as I said, which is on page 76, and this is equation 3.4, which is on page 85. So there's a big, there's 9 pages gap between this statement and this statement. So instead of looking at this as a result of that, I would like to look at this as a starting point. This is the intuitive reason for how I'm going to define the probability of A given B. Okay, so now let's look at some of the consequences of that to try and convince you that this makes sense. First of all, if I look at the definition here, I could say, what's the probability of A given A? In other words, what's the probability that A occurs if I know A occurs? So if I plug into the formula here, I find out that the numerator is the probability of the intersection of A and A, and the denominator is the probability of A, because in what I'm doing is I'm taking this formula and I'm replacing B by A. But the intersection of A with itself is simply itself, so that's the probability of A over the probability of A, which of course is 1, and that makes perfect sense. Okay, so you can see that the effect of this denominator is to make things, is to renormalize, because if I didn't have that, then the conditional probability would be the same as the unconditional probability, which would mean that the new information had no effect. How about this? Suppose that the intersection of A and B is empty. Then the probability of A given B would be the probability of the intersection, which is the probability of the empty set divided by the probability of B. Of course, the probability of the empty set is 0, so the answer would be 0. And that makes sense too, because if A and B have no points in common, if they don't overlap, then if I know B occurred, A can't possibly occur, so therefore the probability of A given B is 0. So it makes sense. Now in the definition, usually they say something like this is the answer if the probability of B is not 0, because if it's 0, then of course you're dividing by 0. But that's a little bit flaky actually, because we'll see later on in the course that you can have the case in which the denominator is 0. Of course then in that case the numerator could also be 0, and so it's the ratio that counts. But for our purposes now, I would say don't worry about it. Just remember that that this is the definition, this is the formula that you use, and what we want to do is we want to look at this from 2 points of view. One is the intuitive point of view, where that's possible, and then look at it from the formal point of view and see that the two things match. And then we'll see cases where the intuitive point of view could be misleading, or maybe it's not clear how you do it, and then you fall back on the formality. And of course that's the whole idea of the subject. In fact, that's the whole idea of any kind of mathematical subject like this. Yes?
So is P of B always going to equal 1?
P of,
P of B, or the probability of B occurring,
no.
always going to equal 1?
Well, the
right?
probability of B, if A and B are the same, then the answer is 1. Because what you're saying is, what's the probability of some event if I know that event occurred? But if A and B are just arbitrary events, then the probability is given by this ratio. What I want to do is I want to convince you that this makes sense. I'm starting out, initially I have the probability of A, and I have the probability of B. That's in the original sample space. And now what I'm going to do is I'm giving you more information. For example, I could say, here's an example. I could say, suppose I toss a coin, and I ask you, what's the probability that I get a head? And you'd say 1/2. Then I said, okay, suppose I toss a coin, and I ask you for the probability I get a head, but I also tell you that I looked and saw what happened. Well, if I saw that it's a tail, then the probability of getting a head is 0. And if I saw it's a head, then the probability of head is 1. So you want to take into account this new information. But it's not always clear how to do that. So the idea of a formal formula is that mathematics allows you to understand problems that you're not smart enough to understand without the help of the symbols. Otherwise, who needs it? Then you just use your common sense. Okay, so let me start with, as usual, examples in which the answer is common sense and show that it agrees with the theory, and then look to cases where maybe it's not so much common sense. So, I want to go back to my typical example of dice. So I have 2 dice, and they take on the values 1, 2, 3, 4, 5, 6. So that's die number 1. 1, 2, 3, 4, 5, 6. And die number 2 has 6 values. 1, 2, 3, 4, 5, 6. That's die number 2. And there are 36 points in the sample space corresponding to the values of die 1 and die 2. And we'll assume that they're all equally likely, because that's the simplest model and there's no reason to assume anything else at the moment. And since there are 36 of them and they're all equally likely and their probabilities have to add up to 1, that means that each of them must have probability 1 over 36. So let me ask first this question. What's the probability that x1 plus x2 is equal to 8 given x1 is equal to 5? Okay, so I have the 2 dice, I roll them, I want to know the probability that the sum is 8, but I tell you that I happen to have peeked at one of the dice and it has the value 5. Okay, so what's this probability? So now I'm just going to apply this formula and show that it gives exactly what everybody knows it has to give. So the denominator is the probability of the event B. That's the probability that x1 is equal to 5. And the numerator is the probability of the intersection of A and B. So it's the probability that x1 plus x2 equals 8, and, I use a comma there, x1 is equal to 5. Now, let me rewrite the numerator, because if x1 plus x2 is equal to 8 and x1 is equal to 5, there's only one way that can happen, namely, it must be that x1 is equal to 5 and x2 is equal to 3. The denominator is the same. So, if the sum is equal to 8 and one of them equals 5, that means that one equals 5 and the other one equals 3. And if one is equal to 5 and the other is equal to 3, then the sum is equal to 8. So, this and this are logically the same, and now I just plug in the values. The probability that x1 equals 5 and x2 equals 3. Okay, so what's that? That's the x1 is equal to 5, x2 is equal to 3. That's that guy right there, 1 point. That probability is 1 over 36. What's the probability that x1 is equal to 5? Well, there are 1, 2, 3, 4, 5, 6 points right here, this set. That represents x1 is equal to 5. So that probability then is 6 over 36. The 36's cancel, and the answer is 1. Okay, that's sort of obvious, because if I ask you for the probability that the sum of the two dice is 8, and I tell you that one of them is 5, then you know that what you're asking for is the probability the other one has the value 3. And since a single die has 6 faces, you would assume that they're all equally likely, then the probability of one of them, namely the 3, should be 1 chance out of 6. So it's common sense. Now, another way to look at it is what's called the reduced sample space method. Okay, so let me write that down. Reduced sample space. And the author discusses this on page 79. And here the argument is, all right, now what am I doing? I'm conditioning on the event that x1 is equal to 5. That's B. So that means that I am reducing my sample space now to a new sample space that consists of only the points such that x1 is equal to 5, and there they are. So in my new sample space, what I've done is I've said that now there are only 6 possible values, and what I'm going to do is I'm going to take the probabilities for those events, which were all equally likely. They were all 1 over 36, so I'm going to keep them to be equally likely, but now their probabilities have to add up to 1. So I'm going to change each one of them from 1 over 36 to 1 over 6, and set the probabilities of all the points outside of B equal to 0. So in other words, I've changed the question now so that the points outside of that circled area, outside of that set, have probability 0. The 6 points inside are all equally likely, so each of them has probability 1/6, and therefore the probability of this particular one is 1/6. So by the reduced sample space, I simply ignore everything outside of B, renormalize, that is, I take the probabilities inside of B and I inflate them so they add up to 1 again, and then I just solve the problem as if it was as if I were starting from the beginning. Okay. So this is common sense. Any questions on this? Let's look at the reverse. Suppose I said, what's the probability that x1 is equal to 5 given x1 plus x2 equals 8? So now I'm saying, okay, I roll 2 dice, and I observe that the sum is 8, and now I ask for the probability that a particular one of them has the value 5. So how does that knowledge that the sum is 8 affect the probability associated with one of the dice? So again, I would apply the same formula. So the denominator is the probability that x1 plus x2 equals 8. And the numerator is the probability of the intersection, which is x1 is equal to 5 and x1 plus x2 equals 8. Okay, now the numerator is the same here as it was there. The intersection of A and B is the same as the intersection of B and A, so the numerator is still the same. So the numerator is still the probability that x1 is equal to 5 and x2 is equal to 3. Okay, the denominator is the probability the sum is equal to 8. I'll write it out. Probability x1 plus x2 adds up to 8. Okay, now, as far as the numerator is concerned, that's the probability associated with that point. What about the denominator? The sum equals 8. That corresponds to the values 2, 6, 3, 5, and so forth. In other words, this set right here is now the set B. So this is the event x1 plus x2 adds up to 8. Now, the numerator, as before, is 1 over 36. The denominator, what's the probability that x1 plus x2 is equal to 8? Well, there are 1, 2, 3, 4, 5 points in the set that corresponds to x1 plus x2 is equal to 8. So the probability of that is therefore 5 over 36. So here's 5 divided by 36. The 36's cancel, and I'm left with 1/5. Okay, how could I have gotten this by common sense? And the answer is, well, now my reduced sample space consists of the set in which the sum of the dice adds up to 8. So that's this thing right here. So now I'm going to make my new sample space consist of just this set right here, and that set has 5 points in it. So they were all equally likely to begin with, so they're still all equally likely, but now each one must have probability 1/5 instead of 1/36. So if I set the probabilities for all the points outside of the set equal to 0, the probability of this particular point is 1 out of 1, 2, 3, 4, 5, or 1/5. So again, this is, you could have reasoned through this with common sense without having any formal definition of conditional probability. And so that, first of all, for one thing, it shows you two things, I think. One is it shows you that the formulas make sense, at least in this application. And the second is, notice that the probability of A given B is not, in general, equal to the probability of B given A. And this causes a lot of confusion, because in probability, when you describe a problem, if it's a real problem, not a mathematical problem, you describe it in words. And so that means, or somehow it's described in words. But in real life, if you're actually an engineer solving probability problems, nobody gives you a statement of a problem like it comes from a textbook. What they do is there's some vague statement out there, and you want to understand what's going on. So if you don't interpret the words correctly, it's easy to get confused between what the event is that's asked for and what the event is that's given. Okay, so in general, probability of A given B does not equal probability of B given A. Now, the book has lots of examples of this stuff, and they tend to be either straightforward or confusing. So you read them and you make that decision. And I'll just do some of these, which I think clarify things like this. So, any questions about this? Okay, so let me pose another question. So, this is a sort of entertaining kind of problem. At least I'm entertained. This is sometimes called the Monty Hall problem. So here's the way it works. You have a game show. Let's make a deal. So that's the name of the TV show. Okay, so we have TV show. Let's make a deal. So this was a show that was popular, I guess, in the 60s. I don't know. I think you can still see reruns on cable TV. And Let's Make a Deal had an MC, Master of Ceremonies, Monty Hall. And the way that the show would work is there would be some contestant, and then Monty Hall would give him some information, and then the contestant would have to make some kind of decision, like whether he wanted to buy something or vote a certain way or choose a certain prize or something of that sort. And it was pretty vanilla stuff compared to today's TV. But in any event, in this version, what happens is there are 3 curtains. And Monty Hall tells the contestant that one of the curtains hides a car and the other 2 curtains hide goats. So let's represent that by CGG. And the contestant knows that there's 1 car and 2 goats, but he doesn't know where the car is and where the goats are. So Monty Hall said to the contestant, okay, pick a curtain and you can have whatever's behind it. So the contestant picks a curtain and he's just about to lift up the curtain, and Monty says, wait a minute, he says, I just can't, the suspense is too much, I can't control myself. And he runs over and lifts up a curtain. And under the curtain there's a goat. And so now 1 goat has been removed, so now there is left a car and a goat, but the contestant still doesn't know which is the car and which is the goat. And then Monty says, okay, I tell you what, I'm going to give you another chance. He says, since I already removed one of the goats, what I'm going to do is, you have a choice. You can either stay with the original curtain that you picked, or you could switch to the other curtain. Which do you want to do? So now the show is really getting exciting, and the audience is getting into it, and they're all yelling, stay, stay, switch, switch. And the poor contestant, he doesn't know what to do, because if he stays, then he looks like he's really stubborn. And if he switches, then he's wishy-washy. So what's a guy to do? So, of course, what he wants to do is he wants to apply conditional probability, because now what's happened is Monty Hall has revealed some information. Originally, the contestant's chance of picking the car was 1 chance out of 3. But now, a goat has been removed, so now there are 2 possibilities, car and goat, so something has changed. So the contestant wants to take into account this new information and make the best possible choice. So, let's see, let me write that this way. Let's write that we have 2 probabilities here. So let me call the first one probability A, PA, and that is the probability that the contestant wins the car if he switches. So I'm going to call that PA. And PB is the probability that the contestant wins the car if he doesn't switch or if he stays. So the question is, which is larger? Is it better for him to switch, or is it better for him to stay? So, being as this is the US of A, Democratic and all that kind of stuff, which is what I like to do throughout the course, we'll put things up to a vote. So, what are the possibilities here? The probability of A is greater than the probability of B, which means better to switch. Better to switch. Another possibility is that the probability of A is less than the probability of B, which means it's better to stay. And the third possibility is that it doesn't matter. Probability of A and probability of B are equal. Doesn't matter. Now, of course, when I say it doesn't matter, of course it matters in the sense that in any particular trial, switching or not switching is going to make the difference between winning and losing. But over the long run, are the odds changed by switching or staying? It's sort of like toss a coin. If you toss a coin and the coin has been tossed but you don't know what the answer is, it's either heads or tails. So if it's heads and you choose tails, well, then you lose. If it's tails and you choose heads, then you lose. If you choose it right, you win. If you choose it wrong, you lose. And so in any case, if you make a choice and then you change your choice before you know what the coin is, you may turn a winning situation into a losing one, or you may turn a losing situation into a winning one. But obviously, from a statistical point of view, it doesn't matter, because if you don't know what the coin is, when you make your choice, regardless of which choice it is, the chance is 50-50, 1/2 that you'll guess right and 1/2 that you'll guess wrong. So these are the possibilities. You improve your chances by switching. You improve your chances by not switching. It doesn't make any difference whether you switch or not. Your odds of winning are still the same. Okay? Okay, so now let the democratic process proceed. How many people think that if you're the contestant, you're better off switching? 1, 2, 3, 4. 4 people think it's better to switch. How many people think it's better to stay? 1, 2, 3, 4. Looks like 5. How many people think it doesn't matter? Looks like everybody else. Let's say 25. Okay, so since this is the majority vote, why doesn't it matter? Anybody want to volunteer an argument here? Yeah.
Take the last one out. Now this is 1 out of 2. This is 1 out of 2. If it goes to the other one, it's still 1 out of 2.
Okay, so you're using the reduced sample space argument, because what you're saying is, originally there were 3 possibilities and they were equally likely. Now there are 2 possibilities and they're equally likely. So the probabilities, instead of being 1/3, 1/3, 1/3, should now be 1/2, 1/2. Right? Okay, so that, and I guess everybody who voted for this agrees with that.
It's assumed that the goats in the car are not chosen at random because then you take into it.
Chosen at random by whom? Well, the contestant chooses at random because he doesn't know where the goats and cars are.
Placed at random, I mean, because the probability of 2 goats in a row is slightly less than.
Well, no, all arrangements have the same probability. So actually, from the contestant's point of view, it doesn't matter whether they're placed at random or whether they're placed in some order, that the person who places them knows what it is. From the contestant's point of view, all that matters is that there is 1 car and 3 choices, and he has to pick one of them. So, but however, it might matter whether Monty Hall knows whether the goat or car is. So, one question is, okay, we said that Monty Hall shows a goat. Why did he show a goat? There's 2 possibilities. One is he showed a goat because that's what happened to be there when he lifted up the curtain. The other possibility is he knows where the car is and where the goats are, and he knows that whatever curtain the contestant picks, there's got to be at least 1 curtain remaining that's a goat. And since this is a TV program, what Monty Hall wants to do is he wants to maximize the suspense. So therefore, he is going to show a goat because he knows where it is, and then the game won't end. Because if Monty showed a car, then the game just kind of fizzles. It's over. The contestant hasn't even made the choice. So when you look at that possibility, then the question is, well, does it matter whether Monty shows you the goat on purpose or whether he shows you the goat by chance? In both cases, he's still showing you the goat. So you can see that there's a little bit of difficulty here in interpreting how you're going to take into account this information. So now what I want to do is I want to analyze this using conditional probability, and so we'll get the answer. Okay, so to do that, let me erase this stuff here. All right, so here's the way I want to analyze it. First, I'll make a matrix here, and I'll have 3, nine entries. Going along the top, I'll have F, M, and R. And F stands for first choice. In other words, this is the contestant's choice. Remember, the contestant, we're assuming, doesn't know what's going on. Then M stands for Monty's choice. And R stands for remaining curtain. We'll define 3 events: E1, E2, and E3. And they're like this: C, G, G. G, C, G, 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 C. That takes into account every possibility. So this says that the first choice, the contestant chooses a car, and then Monty shows a goat, and the remaining curtain has a goat. Or the contestant chooses a goat, Monty shows a car, the remaining curtain has a goat. Or the first choice of the contestant is a goat, Monty shows a goat, the remaining curtain is a car. So those take into account every possibility, and what we'll do is assume that, we're going to make some different assumptions there. Okay, so first let me go back over here and recognize that these probabilities are really conditional probabilities. Because PA, which is the probability that the contestant wins the car if he switches, can be written this way. This is the probability that the remaining curtain hides a car, given Monty shows you a goat. Okay, so what's the probability that the contestant will win the car if he switches? We know that Monty has showed you a goat, so the question is, given that information, what's the probability that he will win if he switches, so that means he'll win if the remaining curtain has the car behind it. Similarly, PB is the probability that the remaining curtain hides a goat, given that Monty shows you a goat. Okay, so I want to recognize that these are conditional probabilities. What I'll do is I'll calculate this conditional probability right here and recognize that, note, PA plus PB must add up to 1. Okay, why is that? Well, Monty shows you the goat, so once you're restricted to that sample space where Monty shows you a goat, that means there are only two possibilities, which is that the remaining curtain shows you a car, hides a car, or the remaining curtain hides a goat. And those events are mutually exclusive, so since their probabilities must add up to 1, PA plus PB must add up to 1. So that means that what I can do is I can figure out what PA is, and if it's 1/2, then PB must be 1/2, and this is the right answer. And if PA is greater than 1/2, then PB must be less than 1/2, and then that's the right answer, and in reverse, then that's the right answer. So to answer the question, I'm going to calculate this using this conditional probability. Now, if there's any objection as I go along, remember, this is typical of probability in applications in that it's not a mathematically stated problem. It's a verbally stated problem, and that means that you have to impose on the verbal situation a sample space and assign probabilities, and of course, if you don't do those things right, then the conclusions are not going to make sense. So you have to make sure that you understand each step. Okay, so I'm going to take PA, which is the probability that the contestant wins if he switches, as the conditional probability, that given that Monty has shown a goat, that the other curtain that remains would hide a car. And this, that the probability that he wins if he doesn't switch, that says, given that Monty shows you a goat, that the probability is that the remaining curtain also shows you a goat, or hides a goat, in which case you would win if you stay, because you would have already picked a car. Okay, so now let me write out what these probabilities are. Okay, so I'm going to write out PA, which by definition is the probability that the remaining curtain is a car, given that Monty has shown you a goat. So now I'm going to apply the definition of conditional probability. So the denominator is the probability of the event B, which is the probability that Monty shows you a goat. And the numerator is the probability of the intersection of A and B, which is the probability that the remaining curtain has a car and Monty shows you a goat. Probability R equals car and, comma, M equals goat. Okay, so that's from the definition of conditional probability. And now we have to plug in what's going on here. Okay, what's the probability that the remaining curtain shows you a car and Monty shows you a goat? Well, that's event E3, because we want the remaining curtain to be a car, Monty shows you a goat. Of the three possibilities, that's the only one that corresponds to that. So the numerator is the probability of E3. The denominator is the probability that Monty shows you a goat, and Monty can show you a goat either E1 or E3, not E2, and those events are mutually exclusive, so the denominator is the probability of E1 plus the probability of E3. And now we have to work out what those things are. So now, there are two possibilities. Because now I claim, when I evaluate these things, these probabilities depend on whether or not Monty knows where the car is and whether he purposely shows a goat or whether he happens to show a goat by chance. So let me write those down here. Okay, so, all right, I'll leave this part here. Okay, so suppose Monty doesn't know. So it just so happens that when Monty picks up his curtain, it happens to be one that has a goat behind it. But it could have had a car, in which case he would have screwed up the whole thing, because then there wouldn't have been any suspense. All right, so what does that mean? If Monty doesn't know, then I claim that the probability of E1 and the probability of E2 and the probability of E3 are the same. And they're all equal to 1/3. Okay, so in other words, Monty doesn't know what he's doing. So therefore, since Monty doesn't know what he's doing, each of these possible arrangements of car and goat are equally likely. So therefore, if Monty doesn't know, then what I would plug in here is 1/3, 1/3, 1/3. Okay, so what I would get then is this. I would get 1/3 over 1/3 plus 1/3. Of course, that's 1/3 over 2/3, or 1/2, which is what most people think. Doesn't matter. Okay. So 1/2 in the case in which Monty doesn't know. All right, so that's sort of common sense, but now the question really is, well, we should impose on this the idea that, or ask the question, suppose Monty showed you the car, the goat, on purpose. Which of course is, the way the problem is stated, that's really what the author of the problem, we'll get into that in a moment, is intending you to think, or to realize, that Monty is not going to just happen to see what happens, just arbitrarily pick a curtain when he's on TV. This is a TV show, so he wants to maximize the entertainment value. So what happens if Monty does know? In other words, Monty purposely does know. The view of most people, though, is what's the difference? In both cases, he still shows you a goat. But let's see what it is. Suppose Monty does know. What's the probability of E1? Well, E1 is the event that corresponds to the contestant first choice picking the car. Now, the contestant, we know, doesn't know what's going on, so the contestant is going to pick one curtain out of 3. The probability he happens to pick this one is clearly 1/3. What's the probability of E2? Well, E2 is this event right here, which has Monty showing you the car. But we just said that that never happens if Monty knows what's going on and is trying to maximize the suspense. So this would never happen, so the probability of E2 would be 0. So what's the probability of E3? Well, since these probabilities must sum to 1, the probability of E3 must be 1 minus the probability of E1 plus the probability of E2. Or in other words, it must be 1 minus 1/3, or in other words, it must be 2/3. So if Monty does know, then the numerator becomes 2/3. The denominator becomes 1/3 plus 2/3. And that ratio, of course, is 2/3, because the denominator is 1. So, if Monty does know, it's DOES. If Monty does know, then the probability that the contestant will win if he switches, PA, I guess I erased that definition, is going to be 2/3, which means if he doesn't switch, the probability is 1/3, which means that he doubles his chance of winning by switching. So if Monty doesn't know, then it doesn't matter. And if he does know, then it's better to switch. Which means, of course, that if you don't know whether Monty knows or not, it's better to switch. Because if Monty doesn't know, then it doesn't make any difference. Nothing is lost here. And if he does know, then, of course, you're doubling your probability of winning.
Double or?
You're doubling. Because your original probability of winning was 1/3. Initially, suppose there were no game here in the sense that Monty gives you another choice. The contestant picks a curtain. The chance that he picks this one is 1/3. Now, if Monty purposely shows you a goat, then the probability that you will win if you switch is 2/3. So therefore, you have doubled your probability by switching. You've gone from 1/3 to 2/3. On the other hand, if Monty doesn't know, then the probability of winning is not 1/3, it's risen to 1/2, but if you switch, it's still 1/2, and so therefore it doesn't matter whether you switch or not. So the answer is, it's better to switch, because if Monty showed you the goat by chance, then it statistically makes no difference. And if Monty showed you the goat on purpose, you're twice as likely to win if you switch than if you stay. So this is very surprising, I think, for most people. Because first of all, most people don't realize that there's two questions here, based on whether Monty shows you the goat on purpose or by chance. Because the information is not simply that he shows you the goat, the information must contain why he shows you the goat. And second of all, even if you knew why he shows you the goat, that is, you knew whether it was by chance or not, it still might not make a difference to most people. They still say, what's the difference? He showed you a goat, that's all there is to it. So the common sense view is that the original chance was 1 out of 3. Monty removes one of the possibilities, so now the chances are 1 out of 2, but it doesn't matter which curtain you choose, it's still 1 out of 2. So that's not correct. So this is a very interesting problem. So it shows you, what does it illustrate? First of all, it illustrates that probability is trickier than you think. Second of all, it illustrates that democracy doesn't work. I suppose we can't say that, but it seems to be the evidence at the moment. But that'll pick up, I hope, by the end of the course, because we'll have educated voters. So that's the key. Like, I guess we'll find out whether Schwarzenegger wins or not. So that'll tell us. Okay, this is actually in the book. In fact, there's a big history to this problem. So first, let me indicate that this is in the textbook. This is exercise or example 3.8 on page 80. And it's also example or exercise 3.27 on page 111. I think this is an exercise, that's an example. This is actually a fairly well-known problem. It was originated around, roughly, I think it was 1990. That's when it became popular anyhow, by Marilyn Voss-Savant. And she writes a column for Parade magazine. And in that column, she has lots of these kinds of recreational puzzles. And when she wrote this one, oh, by the way, she claims that this is her real name. Of course, this is French for genius or seer or something like that. So the chance that she just happened to have a name for genius, and she claims to be the world's smartest woman, or smartest person, in fact. She claims, I think, to have the highest tested IQ, well over 200 points. So that would make her like the smartest person in the whole world. And so my question is, why is she writing a column for Parade magazine instead of finding a cure for cancer? Probably because there's more money in writing a column for Parade magazine. But in any event, This is her, she claims this is her real name, not her stage name. And when she originally published this problem, of course, I'm not sure exactly how it was written, but it was sort of misleading, I think, in the sense that she purposely didn't tell you that Monty Hall would show you the goat on purpose. And so when she wrote her solution, she got lots of letters from people. Well, a lot of them had saying things like, I have a PhD in statistics from Harvard and you're a pile of crap, that kind of thing. But of course she was right. Either the people who criticized her didn't understand this, or they simply overlooked the fact that it made a difference whether or not Monty Hall showed the goat on purpose or by chance. They never even considered that. And of course that's really very important when you do these problems. You have to consider everything. If you don't, then you're not going to get the right answer. You may not get the right answer. So there was a lot of stuff about this, and let me see if I can read something here. Here's a little paragraph I took from the Scientific American. This was written by Martin Gardner, who wrote a famous column for the Scientific American for many years, and this was published in August '98. And he says, a lot of people now I think made claims like this because this is so simple-minded. He says, I introduced this problem in my October 1959 column in a slightly different form. So he talks about having 3 cards or 3 prisoners. And I think in one of the versions there are 3 prisoners, and one of the prisoners has been pardoned by the governor, but nobody knows which one except the guard. And so one of the prisoners asked the guard to tell him not whether or not he has been pardoned, but tell him which other prisoner has not been pardoned. And of course, one argument is, well, what difference does it make? And the other is, well, if the guard knows, then of course he's going to, in a sense, play the role of Monty Hall here, and so therefore the other prisoners will get more information than the guard would think he's giving away. In any event, there are different ways to say it, but the way Marilyn said it, and by publishing it in a newspaper, in a magazine like Parade, with a wide readership instead of publishing it in a textbook or a scientific journal, she made a big splash. So he says, I introduced this problem in my October 1959 column, and he says, in 1990, Marilyn Vassavant, the author of a popular column in Parade magazine, presented still another version of the same problem, involving 3 doors and a car behind one of them. She gave the correct answer but received thousands of angry letters, many from mathematicians, accusing her of ignorance of probability theory. The fracas generated a front-page story in the New York Times. And in fact, there are websites. So if anybody's interested, it's too complicated to write down here, but I have a file which I'll send anybody if you ask for it, which just has some URLs which relate to this problem, or to Marilyn Vassavant. One is the Parade magazine website, and there's one here from Dartmouth. It says Chance Course Topics. Another one is from NPS, which is Naval Postgraduate School. Another from the University of Michigan. Another from Rice University. And something from WISKIT. Maybe that's Wisconsin. I don't know. In any event, you can see that a lot of people are interested in this. So if you're interested, just send me an email and I'll send this file back and you can look it up. Okay, any questions about that?
I look at that and I just don't get it. Why would it be 2/3?
Okay, let's go. Let me give an intuitive reason. The trouble with intuitive reasons is they're very convincing, but they're sometimes wrong. Okay, so I'm going to give 2 intuitive arguments. The first intuitive argument is the one that everybody thought of right away, which is you originally have 3 possibilities, and they're all equally likely. You eliminate one of them, so now there are 2 possibilities, and they are equally likely. It's the they are equally likely part that's incorrect. But if they were equally likely, which is what they would be if the one that was eliminated by chance, not intentionally, then it doesn't matter whether you switch or not, your probabilities are 50-50. Okay, so everybody buys that, but it's right only in the case in which Monty doesn't know. Suppose Monty does know. Okay, if Monty does know, what that means is he's always going to show you a goat no matter what. So therefore, what really matters is what the contestant picks. If the contestant initially picks a car, then since Monty is always going to show you a goat, there will be a goat in the other curtain, and the contestant will lose by switching, or his probability will decrease. The other way around. You can see it's confusing. Let's start again. If the contestant picks a car, then actually no matter what Monty picks, the contestant will lose by switching. If the contestant picks a goat, then if Monty always picks a goat, only a car is left, and the contestant will always win by switching. So the question really depends on what the contestant originally picks. Now the contestant, since he doesn't know what's going on, has a 2/3 chance of picking a goat and a 1/3 chance of picking a car. So if Monty always shows him a goat, then the probability is 1/3 that the contestant will pick the car, and if Monty always shows him a goat, then that means that if he switches, he will lose, which means that 1/3 of the time he will lose by switching, which means that 2/3 of the time he would win by switching, because 2/3 of the time the contestant would have initially picked the goat. Let me say that again because I think I made it more complicated than it is. The probability that the contestant will initially pick the car is 1/3. Now, assume that Monty always shows you a goat. That means that if the contestant initially picks a car is 1/3, then since Monty is always going to show you a goat, knowing that doesn't provide any new information, if he always shows you a goat. Therefore, the probability is 1/3 that the contestant has already won the car. So if he stays with it, his chance of winning is 1/3, and so if he switches, his chance of winning must be 2/3. You have to think about it, but the point is, the intuitive argument is, that if Monty always shows you a goat, then you know that Monty always shows you a goat, so all that matters is whether or not the contestant has originally picked a car. If he has originally picked a car, which happens 1/3 of the time, that means that he will win 1/3 of the time if he stays, and therefore he will win 2/3 of the time if he does not stay. So therefore he should switch. Yes?
The choices were 2 votes in 1 car, and there were like 3 different prizes, and the whole thing would be waiting.
I didn't get that.
You know, it's 2 votes in 1 car, so it's 2/3.
2 goats in 1 car, 2/3,
There
1/3.
were 3 different things, like a car, a goat, and like a middle prize. It'll be 1/3, 1/3, 1/3, and if you take one out, it'll be 1/2, 1/2.
Well, that's hard to say because the idea here is that if Monty's going to show you something on...
1/3 that you're going to win, 1/3 you're going to lose, so it'll still be half that.
It depends on what you mean by win or lose, because if there are 3 things, if you
I
talk...
think that you win the car.
Let's suppose there were 3 things, but only one of them is good to win. I don't know, because then you'd have to say which thing it is that Monty shows you. So that might confuse the problem a little bit. I mean, I'm sure you could work it out, but it does change things. The idea here is that when he shows you a goat, the 2 goats are equivalent. Right. Yes.
Since this is an actual situation that occurred, right?
Say that again?
Since this situation actually occurred and the show was actually on.
Actually, I don't know whether that's true or not. I don't know whether it
Okay,
actually...
I wanted to know if statistics had proven this correct.
Well, now the question is, what does statistics mean if you're going to conduct an experiment only once? See, if Monty Hall played this game over and over again on the show, well, that wouldn't work because it would get pretty boring if it was the same thing over and over again. So when you're talking about probabilities and you're interpreting those in the classical sense, then what you mean is that the probability is a frequency. So if the probability of winning is, say, 1/2, or let's say 2/3, if the probability of winning, if you follow a certain strategy, is 2/3, what that means is if you played the same game over and over again under the same conditions an infinite number of times, the ratio of the number of times you win to the total number of times you play would be 2/3. But if you play the game only once, then it's not clear what probability means. So this, in fact, is an important philosophical point, because lots of actual applications of probability have to do with experiments or things that may or may not, that may happen only a small number of times or once.
I thought this particular situation occurred several times. So that's why
It might have, I don't know, but I doubt that it occurred several times, because I think that Monty Hall would not have played this game more than once or twice, because remember, this is TV and you can't have the same thing over and over again. It would be silly. So my point is that when you're talking about calculating odds or probabilities for an experiment that's only going to occur rarely or once, then it still makes sense to go with the strategy that gives you the highest probability of winning. But you can't interpret it in terms of frequencies. Then you have to interpret it in terms of something smushier, like likelihood or degree of belief or something like that. And philosophers are, to this very day, it's a hot argument as to whether or not, what probability means in the actual case, in applications where you cannot imagine that you're repeating the same experiment infinitely often under ideal conditions. Like when you're talking about what's the probability that Isabel is going to hit a certain area. Well, everybody believes that those probabilities make sense, but nevertheless, we're not thinking about an infinite number of trials with Isabel under exactly identical conditions over and over again, and saying that a certain percentage of the times it's going to hit North Carolina, a certain percentage of the times it's going to hit Florida. That doesn't really make any sense, because you can't imagine this happening over and over again under exactly identical conditions. But it still makes sense to say, yeah, it looks like it's a lot more likely that it's going to hit North Carolina than it's going to hit Florida. In fact, the fact that we're here today means we all believe it's going to hit North Carolina. Is there another question out there?
Yeah.
Yes.
I mean, I was just about to ask that, like, if he's saying for example, if you lift the curtain number 3rd, right? It's a goat in there. The Monty show is a goat in there. So if the contestant is pretty sure that Monty is telling him the right thing, there's actually a goat in there, then it could be like 2/3 or switching the probability. Understanding what I'm saying?
No,
All right.
I don't get you.
For example, there's a one curtain number 3, right? Like the one on the right hand side. All right. The first contestant picked that one, right? And
If the contestant picked that one.
yeah, and
Okay.
the Monty said it's a goat in there.
Wait, Monty doesn't say there's a goat in there. Well, Monty says if the contestant picks this one, Monty picks one other one. Now, if Monty was picking by chance, there'd be a 50-50 chance that he'd pick the car, and a 50-50 chance that he'd pick the goat. But if Monty knows that the car is here and he wants to maintain suspense, he's going to always pick this one. And if he always picks this one, that means that that's always going to be the remaining curtain. So since the contestant has a 2/3 chance of picking a goat, and Monty's always going to show him a goat, that means that the contestant has a 2/3 chance of losing if he stays, and therefore a 100% chance of winning if he switches. Again, I'm not saying that right, I think. If the contestant originally picks a goat, which he does 2/3 of the time, and Monty's always going to show him a goat, then if the contestant stays, his probability of having a goat is 2/3. And he doesn't want to have the goat. So therefore, he's better off switching. It's confusing. Okay, so the way I like to look at it is the contestant has a 1/3 chance of picking the car initially. If you know that no matter what the contestant picks, Monty's going to show you a goat, then what that means is that the probability is 1/3 that the contestant will win if he stays with his original guess. And since there are only two possibilities, once Monty has eliminated one of them, the other one must have probability 2/3. And therefore, he's twice as likely to win if he switches than if he stays.
That's only one interpretation of the problem, right? I mean, that's not the only way that you can interpret it.
No, I think there are two interpretations of the problem. One is that Monty shows you the goat by chance. And in that case, if in fact Monty just happened to show you the goat, then it doesn't make any difference whether you switch or stay. Your probability of winning is still 1/2. But if Monty shows you the goat on purpose, then the probability of winning is 1/3 if you stay and 2/3 if you switch. And therefore, you are twice as likely to win by switching than by staying. So the strategy, the best strategy, is to switch. Because if Monty showed you the goat by chance, nothing is lost by switching. If Monty showed you the goat on purpose, you double your chances of winning by switching. That's the truth. Now, the difficulty is that if Marilyn did not state in her problem that Monty shows you the goat on purpose, then the reader doesn't know. The reader may not factor that in. And so the reader naturally assumes that Monty just happened to show you the goat because the reader is not thinking deeply enough about the question. But how Monty really works, that's beside the point. I mean, this is all made up. But it illustrates the fact that how the information is presented, that is, how you interpret this information, makes a difference. And if you were to write a simulation, computer simulation, in which in case 1, Monty always shows you the goat, and in case 2, Monty sometimes shows you the goat and sometimes shows you the car, and you just throw away the cases of the car, because then the game is already ended, you'll find out that these statistics, these answers are exactly correct.
That inspires me to write that program, because I still can't see it.
Okay, write it and report back. And if you don't get the same answer I got, you got a bug in your program.
What I don't understand is why E1 is 1/3, E3 is 2/3 give, and then E2 is 0.
Okay,
It would seem to
E1,
me that they would be 1/2 and 1/2.
yeah, the reason E1 is 1/3 is because E1 is the case where the contestant chooses the curtain first. And the contestant's choice, we're agreeing, is random. The contestant doesn't know anything. So the contestant makes a choice, and if he chooses a car, then it doesn't matter which curtain Monty chooses, it's got to be a goat. So E1, which means car, goat, goat, that's the same thing as saying what's the probability that the contestant chooses the car, first choice. And everybody agrees that that should be 1/3 because there's one car, 3 curtains, and the contestant has no knowledge of where the car is.
Right, but by the same token, we know that Monty is going to choose a goat, so it doesn't matter what the contestant chooses.
That's right. But if the contestant chooses a car, then what that means is that 1/3 of the time, let me say it again, 1/3 of the time the contestant will choose the car, and 2/3 of the time he will not.
Correct.
So the 1/3 of the time that he chooses the car, that means that in those cases he will lose if he switches.
No.
Well, he has to lose if he switches because he's chosen the car the first time. So no matter what Monty shows him, Monty must show him a goat. So if the contestant has already chosen the car, when he switches, he must switch to a goat.
That's correct, but Monty's always going to show you a goat, so that the 1/3 means nothing.
No, the 1/3 means that the chance is 1/3 that the contestant will have picked the car, which means that in that case, he will always lose if he switches.
Yeah, you mean to say over here like E2, right? Goat, car, and a goat.
That has probability 0
Yeah.
if Monty never shows you a car.
Yeah, so if the contestant choose a goat and Monty, chose a goat as well, so it means that the contestant can eliminate the Monty's choice and he will left with only 2 choices then, and the probability is 2/3 then, right?
I think so. I'm not sure what you're saying. Let me say it again in my own words. Okay, here's the first choice. Monty's choice, remaining curtain. So the possibilities are car, goat, 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 car, goat, 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 car. Now, these are the 3 possibilities. If the contestant chooses, without regard to where the car is, he doesn't know, the contestant has no knowledge, the chance that the event car, goat, goat will occur has probability 1/3. Because 1/3 of the time, the contestant will choose the curtain with the car. So this has probability 1/3. Now the question is, what about these two? If Monty never shows you the car, this never happens, and if this is 1/3, then that must be 2/3.
No, I don't agree with that.
Well, I don't know why not.
Because that event doesn't exist in the sample space, so you only have E1 and E3 are the only possibilities.
Your argument is that if you have n possibilities, each must have probability 1/n. My argument is that that's not true. It's not true that if I have n possibilities, each one must be equally likely. The simple examples we've looked at have that property because we're starting off with the simplest examples. But in this case, Monty's action biases the probabilities. Remember that there's two aspects of defining a probability problem. One is what can happen. That's a sample space. The other is the probabilities associated with those events. I gave you an example of this already. Let me go back to that. Suppose we're looking at the dice problem, and I say that instead of representing the dice problem by talking about what each die takes, I say what the sum of the dice is. So now I'm going to define a new random variable, S, sum, which is the sum of x1 plus x2. And now I ask, what are the values that S can take? Well, here they are. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. As usual, I don't leave myself enough space. 12.
Right.
Okay, those are the possibilities. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But does each of them have probability 1/11? No. This has probability 1/36. This has probability 2/36. This has probability 3/36, and so on. Okay? So if my sample space was simply to say there are 11 possible outcomes when I roll the dice, and I'm going to assign them equal probabilities, anybody who thinks that way, let's meet after class and shoot some craps. But you realize that these events, that is the sum being 2, 3, or 4, are made up of combinations of the values of x1 and x2, and if you assume that x1 and x2 are equally likely, then you get this result right here. But here it's obvious, here it's not as obvious.
I'll write it out with the 9 possibilities and work it out like you would with the dice and see if it makes any more sense that way.
But this one you're talking about?
No, yours down here, there's actually 9 possibilities.
Okay,
Right, you've reduced it to 3.
right.
I'll write it out with 9 and see if it makes any more sense
Okay.
to count it that way.
Okay, you let me know how your program goes. Okay, any other questions? We got about a minute left. Okay, so next time I'm going to start talking about the law of total probability, which is section 3.3 on page 89. I'll just write that down. That'll take up a minute. And then we'll do the same thing. That is, in fact, I'm going to use the law of total probability to convince you that this is in fact correct. Okay, that's next time.